In this lesson, we want to talk about the piecewise-defined functions. All right, so in the last lesson, we talked about some of the most commonly occurring functions that we're going to come across. We examined the graphs, and then we talked about the domain and range. Here, we're just going to go a step further and talk about the absolute value function, the greatest integer function, and piecewise-defined functions in general. So we're going to start out today with the absolute value function. So we have y equals the absolute value of x. Or we could write this as f of x is equal to the absolute value of x. Now, I've already graphed this guy for us so we can see what it looks like. And let me put an arrow here and an arrow here. Those two are going to indicate that they extend in each direction forever. And essentially, you can see that you have this V-like shape. And what's creating this is the absolute value operation itself. If you think about what happens here, we can say that y really equals x if x is a non-negative number. So in other words, if I plug in an x that's greater than or equal to 0, well then y just equals x. That's this part of the graph right here. Okay, we saw this in the last lesson where we talked about y equals x. That's the identity function. Okay, but what happens is if x is less than 0, so if x is less than 0, then y really equals negative x, okay? So what happens is instead of this guy continuing on this path down here, it gets flipped up because of the absolute value operation, okay? So it takes the negative that you're plugging in here for x, and it flips it and makes it positive. So what happens, let me kind of erase this. Let's say I plug in something like a -2. Well, it flips it, and instead of it being a -2 down here, like you would have had with y equals x, well, it flips it up here, and then you get this point there. Okay, so you get -2 comma +2 because it made it positive. Okay, so let's think about some ordered pairs here. This is already graphed, but I want you to see something. So let me make an XY table here. So we see that the lowest point occurs at 0, 0 right here. So a 0 for x gives me a 0 for y. That should make perfect sense for you because the absolute value operation is going to make things non-negative. So the smallest I can make y is by plugging in a 0 for x. If I plug in a 0 for x, I take the absolute value, I get a 0 for y. If I plug in something positive, I'm going to get a positive. And if I plug in something negative, I'm going to get a positive. So absolutely the lowest we can go with y is by plugging in a 0 for x. Now another thing you can consider with this V-like shape, every y value other than 0 is going to be linked up with or associated with two different x values. So in other words, if I pick an x value of 2, it's associated with a y value of 2. So an x value of 2 is associated with a y value of 2. But then also the -2, that x value, is associated with a y value of +2 as well. So again, I can say plus or minus 2 for x gives me a y value of 2. You could do the same thing as you kind of move up the graph. So if you go to 4, you have 4, 4. So an x value of 4 gives you a y value of 4. And then an x value of -4 gives you a y value of +4 as well. So again, that's how you're ending up with this V-like shape. It's taking this line right here, and as you go to the left of 0, right on the x-axis, it's kind of flipping this graph back up. So instead of you having y equals x, when x is less than 0, you have y equals -x. All right, so let's talk a little bit about domain and range. I think it's fairly obvious from looking at the graph that for x values, it can basically be anything, right? And thinking about this from the equation, you always just think about what you can plug in for x. That's your domain, right? What can I plug in? What am I restricted from doing? The answer here is nothing, right? I can do whatever I want. So the domain is all real numbers. So from -infinity to +infinity. Then for the range, okay, for the range, what am I going to have? Well, now I'm constrained because this absolute value operation is going to make things non-negative. So the smallest it can be is 0, and then anything out to +infinity. And again, you can see that clearly graphically. If I look at my y-axis, the lowest point here is going to be at 0 on the y-axis. So my lowest y value would be 0. And then, of course, it extends out indefinitely going up. So it's out to +infinity. All right, now let's go through kind of the definition of a piecewise-defined function. So let's again stay with f of x equals the absolute value of x. And essentially what happens with a piecewise-defined function, or some people will say just piecewise function, some people will say split definition function, essentially with this type of function, it's defined by different rules over different intervals of the domain. So I kind of already showed this to you earlier. So essentially you could say y is equal to this absolute value of x, which kind of splits into two different rules. If x is greater than or equal to 0, then really y just equals x. So I can say it's just x if x is greater than or equal to 0. And then really it's the negative of x if x is less than 0. Because again, what happens is if I have a positive number or 0 that I plug in there, I just get the same thing for y. So if I plug in 6, I get 6 for y. If I plug in 144, I get 144 for y, right? So on and so forth. But if I plug in a negative there, I take the negative of the negative. That's why you have a negative out in front of that, and you end up with a positive. So if I want to plug in a negative 144 there, again, all I say is it's the negative of negative 144, and I get 144 as my output or my y value. So this is an example of a piecewise-defined function. It's got different rules over kind of different intervals of the domain. Here we have one rule where we're kind of at 0 or to the right of 0, and another rule if we're to the left of 0. All right, so let's look at another common function that you're going to come across. This guy is called the greatest integer function, and it's also known as the floor function. Essentially, the greatest integer function is going to pair every real number x with the greatest integer that's less than or equal to x. So when we think about this guy, the floor function is actually a better name, in my opinion, because what you're doing is you're actually rounding it down to the nearest integer. Sometimes you hear greatest integer function, you get a little bit confused about what it's doing. So we have y equals the greatest integer of x here, and there's a few different ways we can write this. Let me just start by saying it's f of x equals, I can use the brackets here around x to indicate this. You might also see these kind of lines drawn in. Okay, that might be a way that you would see it. Another way you would see it, this is pretty common as well, you'll see something that kind of looks like an L. Essentially, it's a bracket where the top part's cut off. So all of this is doing is just telling you that you have the floor function. Okay, this is for the floor function, or again, the greatest integer function. For the purposes of what we're going to do today, I'm just going to use the brackets. So let's think a little bit about what happens here, and then we'll look at the graph. So if I plug something in for x, again, it's going to round it down to the nearest integer. So let's say I plugged in 2.5 as an example. Well, just think about which two integers this guy is between. It's between 2 and 3. So it always rounds it down, so it's going to round it down to 2. If I plugged in something like, let's say 1.7, okay, 1.7. A lot of people make the mistake and think that it's going to round normally. It always just rounds down, okay? So it's going to round down to 1. So we can really write some rules here to kind of define what's going on. And you're not going to write all of them because there's an infinite number, but let's just write a few. We can really say that if x is, let's say, greater than or equal to -1 and less than 0, then what's going to happen? If I'm in that range, it's going to round it down to -1, right? So we can say that our f of x here is going to be equal to -1. If x is now greater than or equal to 0 and less than 1, again, if I'm in this range, I'm going to go round down to 0. So here, f of x will be equal to 0. And we can continue this pattern. So if x is greater than or equal to 1 and less than 2, again, it's going to round it down to 1. So f of x will equal 1. So let's think about this graphically now. So if we think about, let's just start with values that are greater than or equal to 0 and less than 1. So if we kind of come here and say, okay, if I choose a value for x that's 0, I know y is going to be 0. So let's just say we have that point 0, 0 that's filled in. Now, as I choose values for x that are larger than 0, but not 1, okay, not 1, I'm just kind of filling this in because I'm staying at 0 for my y value. Then when I get to an x value of actually 1, what happens is my y value is now going to be 1, so I've got to jump up here. So when x is 1, y is 1. So that's why that's filled in, and this is not filled in. And then again, it continues. So y is going to be 1 as we increase x, going up to but not including 2. So that's why that's not filled in. We've got to jump up here. If x is 2, now y is 2. And again, it's always going to be 2 up to the point where we get to 3. Then I've got to jump up here. And again, this process continues forever and ever and ever, and also going down here as well. So that's why you see these 3 dots here and these 3 dots here. That just tells you that the pattern continues forever. It's similar to seeing arrows when you're graphing a line or some other kind of shape. Now, let's talk a little bit about the domain and range. Let's talk a little bit about the domain and range. Let me erase all of this so we can write that in. Let me put this back. Okay, so what's the domain and what is the range? Well, the domain is all real numbers because I can plug in anything for x. I'm not restricted there. So it's going to be from negative infinity to positive infinity. But for the range, I'm always going to get an integer value. If I plug in an integer for the domain, I get an integer. But if I plug in something that's not an integer, it gives me an integer, right, as an output. So the range, we could say, is the set of all y such that y is an integer, okay? So that's one way to write that. Now, let's talk about something else real quick, and then we'll look at a few more of these. We want to talk about the fact that there's something known as a discontinuity in this graph. So this is a concept that you're going to need to know for calculus, and in fact, you're going to get a much more advanced definition when you get to calculus. But essentially, a function is continuous over an interval of its domain if we can sketch the graph of that interval without lifting the pencil from the paper, okay, or a pen or whatever you're using. When you get into calculus, again, you're going to get a more advanced definition that generally is going to involve limits. There's some other ways to think about it too. But for now, this is going to give us a basic understanding. So when a function is not continuous at a given point, we can just say that it has a discontinuity there. So notice how when the greatest integer function is graphed, again, we've got to keep picking up our pencil. I start here, I go here, I got to pick up my pencil, start here, go here, pick up my pencil, start here, go here. So everywhere there's an integer value for x, I have a discontinuity. All right, let's look at another example of a piecewise-defined function. And what I want you to do here, and this is a common task, we want to look at the graph and we want to determine the domain and range, and we also want to come up with kind of the rules that are associated with this function. So what we can see here is that there's a discontinuity at x equals 2. Here's x equals 2. You see that if you were graphing this guy, you could graph this going down. You're not lifting your pencil. And then all of a sudden you get here and you got to pick up your pencil and come up here. Okay, so there's a discontinuity at x equals 2. So what this shows me is that there's some kind of border here where essentially you have one rule on one side and another rule on the other. So if I'm writing a rule, I can say f of x is equal to, and let me just kind of put a bracket in there. So let me do that. So on one side, again, the border is 2. So I know this guy is including 2 and this guy is not. So we'll say one rule is where x is less than or equal to 2. And then another rule is where x is going to be greater than 2. Okay, so those are the two scenarios we're considering. Now, they're only going to give you stuff at this point that you know how to find. So you can see that this guy is basically a line and this guy is a line. So we just need to figure this out. Again, from slope-intercept form, this guy is going to cross at -2 on the y-axis. So if I have y equals mx plus b, this guy crosses at -2. So I know my b is -2. And we have y equals, what's m? Well, to get from this point to this point, I go up 1, 2, 3, and to the left 1. So it's -3 over 1, which is just -3, right? So I have y equals -3x minus 2. So essentially, my f of x or my y is equal to -3x minus 2 if x is less than or equal to 2. So -3x, let me kind of slide this down a little bit. And let me move this down. And I can just say -2. Okay, so what about this guy over here on the other side? We don't have a visible y-intercept, but that's okay. We can still go through and figure this out. We can see that our slope here, if I start here, I would go up 1, 2, and to the right 1, 2. So the slope is 1, right? It's 2 over 2. So y equals 1x plus, what's the y-intercept going to be? Well, I can continue with this slope. I can just go down 1 to the left 1, down 1 to the left 1, down 1 to the left 1. I know that I would impact the graph here, right? You can see that that would be the case. That would be that line. So the y-intercept would occur at y equals 4, okay? So this would be a 4 here. So essentially what I'd have is y or f of x equals x plus 4. So x plus 4 if x is greater than 2. Okay? Now, let's copy this real quick. And we're going to look at another task that you'll come across. And then we'll come back up and talk about the domain and range. So you might be asked to kind of evaluate this guy. And so you'll have f of 3, f of 0, and f of negative 1. Essentially, what you have to do is go through and think about, where do I fall in the domain? If I have f of 3, does 3 fall in the category of less than or equal to 2 or greater than 2? Well, it falls in this category here, so I follow this rule. So f of 3 is equal to 3 plus 4, which equals 7. And that's something you can verify on the graph. If I go back up and look at 3, this is an x value of 3, I have a y value of 7. Okay, so that's true. Then we look at the next one, which is f of 0. So f of 0. So now I'm in the category of here, which is less than or equal to 2. So I have negative 3 times 0 minus 2. Negative 3 times 0 is 0, so I just have negative 2. And I can verify that when x is 0, I do have a y value that's negative 2, right? That's negative 2 right there. So let's go back. For the last one, we have f of negative 1. So f of negative 1. And again, I'm in this category here. So I'd have negative 3 times negative 1 minus 2. Negative 3 times negative 1 is going to be 3. 3 minus 2 is going to be positive 1. And again, we can check that. So f of negative 1, that's here, and that is positive 1. So we're good to go on that. All right, so let's think about the domain and range for a second. That's something that does trip students up. So the domain and the range. We're going to look at the graph, and then we can also verify that by looking at these kind of pieces here. So for the domain, a lot of students incorrectly say that 2 is not included. That's wrong. You go to the left forever, you go to the right forever, 2 is included, it's included right there. The kind of closed circle means it's included, the open circle means it's not. So every real number is going to be part of the domain, including that 2. So from negative infinity to positive infinity. Now, the range is going to be limited. It continues up forever here, and it continues up forever here, but the lowest point is right here, right, where y is negative 8. Okay, so I can see that negative 8 is included, and it's out to positive infinity. And looking at the equations here, this should make a little bit of sense. So we know that if x is greater than 2, we use this guy, so x plus 4. I can't plug in a 2, but if I did, I would get 6 here. And then anything larger than 2 would give me a larger result, so this guy is going up. Now, if I think about the lowest I can make this negative 3x minus 2, what happens is, the smallest I can make this is actually when x is 2. If I plug in a 2 here, negative 3 times 2 is negative 6. Negative 6 minus 2 is negative 8. If I keep decreasing x going this way, you can see that y is actually increasing, right? And the reason for that is because I'm multiplying a negative times a negative, so that gives me a positive, and then I'm just subtracting away 2 from that. So as this negative gets bigger and bigger, the result of this is going to get larger and larger, so that's why this guy is increasing as we move to the left on the x-axis. All right, let's go ahead and look at one more of these, and then we'll just kind of wrap up the lesson. So let me put an arrow here. So this one's a little bit more tricky. It involves a lot of different stuff. So you'll notice that in this case, we have a discontinuity here at x equals 0. Again, if you were graphing this, you would have to pick up your pencil here and jump up here. And then you have another one where x equals 3. If I was graphing this, I'd have to stop here and jump up here, okay? So we know that there's kind of 2 different borders involved here. So we'll have f of x is equal to, let me kind of make my rule here. So we know that one of these guys, let me kind of slide this down because I'm going to need some room. We know that one of these guys is going to be where x is less than or equal to 0. So if x is less than or equal to 0, another one is going to be if x is what? It's going to be equal to 3 and then less than that up to but not including 0. So we could say it's greater than 0 and less than or equal to 3. So that's going to be another interval. And then lastly, we would say if x is greater than 3. Okay. And let me use different colors here, make this a little bit better. So I'll say if, and then I'll say if, and then I'll say if, right? 3 different colors. So 3 different intervals we're going to be working with. Let me make this a little bit better. So what are the rules here Well, essentially, if x is less than or equal to 0, I'm dealing with this graph here, okay? And this shape here, you might remember from the last lesson where we talked about a parabola, the y equals x squared, right? So f of x is going to equal x squared. You can see that because, again, if you start with 0, you get 0. If you plug in a -1, you get 1, right? So if I took -1 and squared it, I get 1. If I plug in a -2 and I square that, I get 4. If I plug in a -3 and I square that, I get 9. So you just have to go through a few points there, and it becomes obvious that they're taking the x value and they're squaring it to get a y value. So this is f of x is going to equal x squared if x is less than or equal to 0. Now, when x is larger than 0, up to and including 3. So 0 is not included here. You see that's why there's an open circle. 3 is included. That's why that's filled in. You have just a straight line here, and it's a horizontal line. So y is constant there. It's just equal to 3. So f of x is just equal to 3 if x is greater than 0 and less than or equal to 3. That's all it is, okay? Then what happens is if x is greater than 3, okay, that's why this is, again, not part of this. So if it's strictly greater than 3, we have this here. Again, I don't know what the y-intercept is, but I can determine the slope pretty easily. I can look at this and say I'm going up 1, 2, and to the right 1. So I would have y equals 2 over 1, or 2 times x, plus, what would my y-intercept be? Well, if I continue moving down, I would go down 1, 2, to the left 1, down 1, 2, to the left 1, down 1, 2, to the left 1. Okay, so that would be my y-intercept. It would occur at -1 on the y-axis. So I could say 2x minus 1 would be my rule here. Okay, and it's hard to kind of fit this in, so let me just slide this down a little bit. So I'll say 2x minus 1 if x is greater than 3. So these are our rules here. Again, x squared if x is less than or equal to 0. It's going to be just 3 if x is greater than 0 and less than or equal to 3. And then it's going to be 2x minus 1 if x is greater than 3. Okay, let's again take this and evaluate some stuff, and then we'll look at the domain and range. So f of -2, how could we find that? Again, figure out where it comes into play. So that falls into this category where x is less than or equal to 0. So f of -2, I'd plug in a -2 for x and square it. F of -2 is going to be -2 squared, which is 4. Again, you can verify that. Here's -2, here's 4. This is -2 comma 4 on the graph. Now, the next one is f of 1. So f of 1, and that falls in the category of being greater than 0 and less than or equal to 3. So here it's just 3, right? And you can verify that again by just looking at the graph. Here's 1. If I go up, I'm at 1 comma 3. That's where I'm going to be. All right, let's look at the last one. So f of 7 is going to be what? Well, in this case, if x is greater than 3, I fall in this category. So it's 2 times 7 minus 1. 2 times 7 is 14. 14 minus 1 is 13. So I'd have a y value of 13. Now, we don't have that value on our graph, unfortunately, because it stops at a y value of 10. But if it did, you could verify that, and you could do a computer-generated graph if you wanted to and verify that. All right, so let's think about the domain and range and just kind of wrap things up here. So the domain and the range. So again, the domain is going to be all real numbers, okay? Because this is going to the left forever, this is going to the right forever. Again, where you get confused, let me kind of erase all this stuff I drew in. Where you get confused is these open circles here, they throw you off. Notice how you have this guy's closed at x equals 0, this guy's closed at x equals 3. So we do have 0 and 3 represented on the graph. It's just that we jump in each case, right? There's a discontinuity at each of those. So the domain, again, is all real numbers. So from -infinity to +infinity, we're covered. For the range, we are limited, right? So what happens is the smallest value here is 0. Okay, we can see that from the graph. And then a lot of students get this messed up as well because they see this open section right here and they think it's not involved. It's involved here in this graph there. So it is covered. And then it's going all the way up from there. So you're covered for every y value from 0 out to +infinity. So that's going to be your range, okay? So you can say the domain here is all real numbers and the range is from 0 to +infinity.